Hello, everybody. We are in chapter 8. So we're starting to get to some of the good stuff, some of the more interesting topics in stats in this course, some of the real world uses. This chapter, along with next chapter, are very much involved in some real world stats. But okay, so chapter 8. Chapter 8 is called confidence intervals. And we're going to get into the notes in a second here, but I just want to know the goal, right? I just want to recognize the goal. The goal is to estimate a parameter. And what's a parameter? We're thinking like mu, sigma, or p, right? Something that describes a population. Because even think about it, if you were trying to find the average height of your high school, it would be super frustrating to go around and ask everyone. Or average weight, or average anything, average GPA. Well, that's probably in the computer. But any sort of height or hair length or anything like that that you calculate average of would be very annoying. And that's just your high school or community college. Imagine dealing with, you know, California or the city of Huntington Beach or the city of San Francisco or LA even. It would be very, very difficult. So instead of getting an exact number, we want to get a pretty good guess, right? And we can get this good guess, but we also can't be that sure. So we're like, hey, I don't know what it is exactly, but I'm going to tell you that mu is between this number 1 and this other number 2. Right? And then maybe we do the same thing for p. P is between this number 1 and this number 2. And we actually, in this book, don't deal with sigma. Most books don't. It's more difficult. It takes too long. It doesn't really. It's not that useful under than very very specific situations. But you can see how it could be useful to know the proportion of people that do a certain thing or maybe vote a certain way, right? Hey, the proportion of voters that are going to vote yes is between 35 and 55%. Oof, I want to get that interval up, right? So that's our goal. We're doing the best we can scientifically to give me an approximation, not exact. And the general formula, this is called a confidence interval. A general formula looks like this. You have your initial guess, the center of your interval, plus or minus some cushion for mistakes. Right? I don't want to say it's going to be exactly this because I don't have all the info. So I give a good guess and then be like, plus or minus a certain amount. So that's what we're building. What is the best initial guess and what's the best way to calculate this cushion for mistakes? All right, well, let's look at this. So in this course, we're actually going to start on chapter 8, section 2. We're not going to worry about section 1. It's not very practical in the real world, and I'll explain why in a second. But we're looking at a point estimate, the sample mean x bar, which is a point estimate for the population mean mu. And point estimate, really what you can call it, the point estimate is it's about the same thing as an initial guess. Right? If I want to find the average height for all the students, let me find an average height for some of the students, right? X bar to at least get a jumping off point. That's the idea. Okay, so we're talking about pennies. I think we've talked about pennies earlier in this course, but whatever. We're talking about pennies. We got 17 randomly selected pennies, right? And let's suppose we talked, they're random. Everything in the rest of this book, honestly, is really dependent on how random things are. So estimate the population mean weight for pennies. Okay, so we can do that. And you can put that in your calculator, run one of our stats, which I've already done here. And when I calculate the mean here, X bar is 2.464. Okay, fine. So now, is that the exact weight or the exact average weight for all pennies in existence? No, probably not. But it's a good jumping off point. Not exactly mu, but whoa, but a good start. So that's that point estimate. So now I want to add or subtract by a certain amount. And I could add or subtract by a random amount, and that'd be fine. Maybe I go up 0.2 and down 0.2. So I can maybe do this. Maybe say mu is between 2.264 and 2.664. And I'm probably correct. But can I do better? Can I tighten that up? Can I be more scientific about it? But that's the goal. I started there, went up 0.2, down 0.2, and we're checking it out. But and this process is called a confidence interval. Our population is normal, called a confidence interval. Okay. So before we jump forward in the notes, just want to mention something. I said I want to be a little bit more sure, right? This guessing game is just never good for any sort of science. But what if I said I wanted to be 95% sure? That number should really jump in your head. It should be, 95%. Why is that familiar? Well, if we're normally distributed or bell-shaped, we follow that empirical rule. That means I go up 2 standard deviations and down 2 standard deviations. So 95. Oh, sorry, got a little frozen here. Give me a second. There we go. 95% confident implies up about 2 standard deviations. Up and down about 2 standard deviations, which we can totally do. So what I could do, and let's just do this. I kind of spaced this out wrong. You don't need to really write this down. What I could do is say, all right, well, X bar plus 2 times the standard deviation for X bar, sigma sub X bar. Now we did that in, I apologize. We did that in our last chapter. What is sigma sub X bar? Sigma sub X bar, remember, is sigma over root n. Okay, perfect. So let me just take sigma over root n, find the 2, and then call it a day. 2 times sigma over root n. But remember, sigma is also a population value. So it's really, really weird that I would know sigma, but not know mu. And the whole point is that I don't know mu. I'm guessing mu. So to use sigma to guess mu is kind of weird, because to get sigma, I needed mu. So that really doesn't work out for us. So I'm like, well, that's fine. Instead of sigma, the population standard deviation, let me use S, the sample standard deviation. Well, turns out this is a problem, because when I use S, 95% does not correspond to 2 anymore. 95% corresponds to a different value. Kind of annoying, but it's something that we have to deal with. So this different value follows a t distribution. Instead of a normal distribution, when I don't know sigma, I follow a t distribution, which is right here. So you can see it's very, very close to normal. So it says, suppose that a simple random sample of size n is taken from the population. If the population is normal, the distribution of x bar follows the t distribution. So ever so slightly different. And look at it. When n is 15, it's this little pink line. So all that's different from the normal is this little itty bitty space right there. But it does matter. But unless you're dealing with small amounts of n, you really don't notice. So it actually took a really long time for people to discover this. It was a brewmaster at Guinness, not that any of us are drinking right now, but it's a brewmaster at Guinness that figured this out because they were doing statistical analysis on some beers and the numbers were always off. But Guinness was super secretive about their like recipes and everything. They did not allow the worker to publish the data under his name. So that's why it's called students t distribution. But anyways, in order to deal with mu, the confidence interval for mu, we need a t distribution. So there's only one standard normal distribution, a z distribution. But for a t distribution, it's different for different degrees of freedom. And degrees of freedom is n minus 1. It's centered at 0, symmetric about 0. That's not weird. Area under the curve is 1, also not weird. The area in the tails is a little bit bigger than the area in the tails of the standard distribution. So that's where we really get the discrepancy, is in the tails. And then, whereas most of our data in a normal distribution is within 3 standard deviations, for a t distribution, most of our data is within 10 standard deviations. So that's that there. But anyways, so to get this estimate, to talk about the estimate, confidence intervals for the population mean are of the form x bar plus or minus t alpha over 2 times s over the square root of n. This t alpha over 2 is the number of standard deviations. And this s is the standard deviation. So we need some sort of calculation to figure out the number of standard deviations. And the way we do this t alpha over 2, is with this small calculation. T alpha over 2 equals inverse t, which you've seen in your calculator, inverse t, alpha over 2, comma, degrees of freedom, which remember is n minus 1. So next thing we need to know, what the heck's alpha, right? I think we briefly mentioned it before, but we need to figure out what alpha is. So let's, we'll reference that. But the value after that plus or minus number is called the margin of error. So the margin of error, of error, that cushion for mistakes is t alpha over 2 times s over root n. And that alpha over 2 is a subscript. I might not be writing it that well. the T alpha over 2 should be a subscript. So that's that there. But again, what the heck's alpha? Well, alpha is the leftover. When you're talking about your confidence interval. So if I'm 95% confident, so if I have my confidence level, and I have alpha over here, 95% spits out an alpha of 0.05. So the leftover from 95% in the tails is 5%. Change it to a decimal. 90%, 0.10. Right? And I'm sure you can figure it out from here. 80%, 0.20, 98%, 0.02, things like that. Okay. So there is the by hand formula. You have all the calculator functions. We can find all of that by hand. But if we don't have to do something by hand, let's not do something by hand, right? So we are going to talk about the technology approach. So basically, we're not doing the classic approach, the by hand approach. No, thank you. The technology approach. So first things first, check normality. It's the same normality as before. Either n is greater than 30 or the population is given normal. And now we do have another check that's possible, or no outliers in the box plot. If there's no outliers in the box plot, we are also in good shape. Fine. The next step is find the interval. We're saying mu is between two numbers, number 1 and number 2. And then, and the way you do it is, so that's what we're doing. We use T interval, and I'll show us where that is in a second. And then write your answers in a meaningful sentence. So this sentence should look something like this. We are blank percent confident confidence. The mean, oh boy, sorry about that. The mean is between, well, the mean, whatever we're talking about, is between blank and blank. Okay, so, I went over that kind of fast. I was jumping around a little bit. Maybe it didn't make that sense, but let's give an answer. How much do pennies weigh? That's what I want to know. I can't give you an exact answer, so I'm saying give me a confidence interval. Fine. This is garbage. Don't worry about that. I don't know why that's there. So what I'd like you to do is put this all in L1 or whichever list you'd like. So press pause. Sorry, hit my knee. Press pause and go ahead and enter that. Okay, so you can see my calculator here. So also real quick, the inverse T, in case you did want to do things by hand, is sitting right here. Second distribution, right under the inverse norm and normal CDF. But anyways, to get to the interval, we're going to click stat, which we've definitely done before, but then go over to tests for the first time. So we're going to use these tests at some point, but we can see here T interval. And I calculate that. Okay. So notice that there's this little toggle option between data and stats. If you have raw data, which we do, we click the data option. Then it says, hey, where's your data? My data is in L1. So enter whatever list your data is in. The frequency, how many times was each data point entered? If you have data organized like that, you can do it that way, but usually the frequency is 1. And then the confidence level for us was 0.99. We do have to enter that in decimal form. So 0.99. Then you click calculate. And then look, right at the top in that parenthesis is our answer, 2.4516 and 2.4767. That's what we're thinking about. So now I include that in my notes. So I get to say now that mu is between 2.4516 and 2.4767. That's what the calculator told us. T interval. Spat that out. And then I write a conclusion saying, we are 99% confident the mean weights of pennies is between 2.4516 and 2.4767 grams. And now this is way better than my guess earlier. Because before I said it was between 2.2 and 2.6, if I recall correctly. When we were just guessing around 2.2 and 2.66. Yeah. Just using some science, using some normal distribution or t distribution now, we get to say something with confidence. And it's a much, much smaller interval. So kind of neat. Kind of neat. But something I'll mention is if this were an in-person class, I would have marked you off here. I would have marked you off because we needed to check if it was normal. So what you might have done is just very quickly, and you can see it in my little camera, is look at the box plot. Box plot, I got it for L1. Cool. Zoom 9. Zoom 9. No outliers. So I'm all good there. So there really should be a little thing up here that says no outliers in box plot. Check. There's usually not a space for that in my open math and on the quizzes. So you don't have to worry too much about that, but just remember there are conditions. Things do need to be normal still. It's very, very important. Okay. So now let's try it again. Same exact problem. I just don't have raw data this time. So I look at it. And, press pause. And I would really recommend pressing pause and giving this a go. But without further ado, I'm going to go ahead and do this for us or with us. So I go stat, edit. Nope, I don't need that. I apologize for that, but I do go stat, go to tests, and I'm doing a t interval again. And now I look at my data. I don't have raw data anymore. I have stats. And it says, what's X bar? So I read through this, and it says there, the sample mean was 8.2. I know you can see the notes on my screen, but you can see it on your screen. The sample standard deviation 9.84. How big's N? 1, 1, 2, 3. And the sea level in this case we want is 95. It's the most common one. We tend to deal with 95s, but that's how that looks. And then calculate. And then now I just write it out, just like before. So let's try it. And remember, I do need that normal condition, and I get to say here n is 1, 2, 3, which is greater than 30. Check. No problem there. We ran t interval. And it told us mu is between, and you can see it in the camera, 9.9617, 6.4383. And then we write this conclusion, which we're saying we are 95% confident. Got a little frozen like usual. Confident. The mean number of hours is between 6.4383 and 9.9617. Hours. Oh, I said number of hours. So that's confidence intervals, right? That's confidence intervals there. So I hope that makes sense. Procedurally, they're not that bad. Maybe, it's a little bit weird, like conceptually what's happening, but getting the numbers should be very manageable here. And that's the main problem from this chapter. When we get into 8.3, it's going to be something very, very similar. But before we get there, there's a little side problem. There's a little side problem. And basically, what if I don't want to ask so many people? If I don't want to ask so many people, but I do need that interval to be tight. The more people I ask, the tighter my interval gets. But I also don't want to waste time and resources. So it's like, oh, just ask 1,000 people. It's like, who's got the time for that? So if I know what my interval, what my margin of error needs to be, I need it to be this tight. Like let's say it's some sort of medical test, some sort of new drug. Like the FDA probably has specific plus or minus numbers, specific margins of errors that they deem appropriate. So if I know that's a margin of error I need, and I want to be 99% confident, it's medical stuff, so I can't just be 80% confident. How many people do I need to ask? Because again, it wastes money. It wastes time if I ask too many people. So to get that, I rework the margin of error formula and end up with this. N equals Z alpha over 2. I assume I'm dealing with normal data because I assume I can find sigma. And then sigma times the margin of error. Okay? And sometimes that sigma is S. But for us, we're going to say it's sigma. And also to be the most clear, Z alpha over 2 is, nope, that's wrong. Z alpha over 2 is inverse norm alpha over 2, comma 0, comma 1. And it is the absolute value of it. Is the absolute value. So I look at this. I look at this problem here. Back to pennies. How large of a sample would be required to estimate the mean with 99% confidence, but I also want to be within 0.005 grams. I don't want to be that far off. Over here, I'm off by, let's see. 0.02 grams, which is fine. But let's say for whatever reason, I need to be within 0.005 grams. Okay, fine. So sigma, it says right there, 0.02. The margin of error, it says right there, is 0.005. Sweet. And then now all we need, the only other piece we need is the z alpha over 2. Well, what's alpha? Alpha in this case is 0.01, which means alpha over 2 is 0.01 divided by 2, 0.005. So z alpha over 2, sorry, just 0.05. Oh no, 0.005. That was correct. And that's a coincidence, by the way, that these are the same. Coincidence. I would say with decent confidence that never happens. Just this one silly example. So z alpha over 2 is inverse norm, 0.00501. And I do this in my calculator. I go to inverse norm. We've used that before, so it's not that weird. So you can see I have it here. You're looking in the camera, inverse norm 0.00501. If you have an older calculator, you might have to type it out like this, 0.005, comma 0, comma 1. And again, I take the positive version of that. So it'd be 2.58. 2.5. Well, let's just say 758. Let's round to 4 decimal places. Try it again on your calculator. Make sure you're getting that. But now I just plug it into that formula. N equals 2.5758 times 0.02 over 0.005 squared. Multiply that out. And you get 106.16. But since we're talking about people, and you can't have 0.16 of a person, to be sure that we hit the desired value, we round up. Right? The more the merrier in reality, but also the more expensive. But we can afford an extra one, so we just round up. So the answer here would be 107 pennies. To get a proper, real tight confidence interval within a 0.005, we need to at least sample 107 random pennies. That's the deal there. So now we need to do the same thing with proportions. But I think I'm going to do that in a different video because this one got a little bit longer than I'd hoped. So I'll stop here.